Yeah, okay. Yeah, the title of the invited talk is Catching and Metal Controlled Properties of the Hybrid Hypophosphorite Perovskite, presented by Professor Gagor from Poland. Please let's start your presentation.
So good morning, everyone. I apologize for these technical problems. And Miriam, thank you very much that you were able to start your talk earlier. So the changes in program won't be so huge. So I will talk to you from the Wrocław, where I work in the Institute of the Low Temperature in the Department of Structural Research. Here, by using the conventional X-ray diffraction, I study organic and inorganic compounds mainly, which have a disorder nature, and I'm investigating the phase transitions and study the structure property relations, searching for new functional materials like multiferroics or optically active. I work with my colleagues from the Institute and also from the University of Technology from Wrocław. And the main person here is Professor Mirek Mączka, who does almost all synthesis and who also serves his concepts and keeps the group together. The topic of my presentation is focused on hybrid hypophosphate perovskites, but I hope that you don't mind if I extend a little bit this subject also to some halides, formates, and I finished with hypophosphate perovskites, just to give you a slightly larger overview on organic inorganic materials. But first, I'll start with the inorganic archetype, which is calcium titanite, perovskite, a mineral perovskite, which was discovered by German mineralogist Gustav Rose, and named after the Russian Minister of the Foreign Affairs, Lev Perovsky. And it was discovered in the Ural Mountains. You can see a probe of this natural occurring perovskites. But the main characteristic of this the compound is its very easy crystal structure, which consists only of 3 components, 2 metal, which are placed on A and B sides. And you can see here a crystal structure, and the main part are these octahedra. So metal ions at the B sides are octahedrally coordinated, and these octahedra form 3-dimensional substructure, which is connected through the corners. And in this substructure, we have larger cavities, which may adopt larger cations. And among oxide perovskites, inorganic perovskites, there are several materials with feature fantastic properties like ferroelectrics, very nice ferroelectric, piezoelectric, pyroelectric, superionic, superconducting materials. So a very nice family of very useful compounds with useful properties just by mixing the B and A metals. So just mixing B and A metal sites. But what will happen if we change the oxygen to some other ion? Or what will happen if we change the oxygen to even more extended species, more extended ion? As examples of these ions, of these ligands, which may be substituted for oxygen, are listed here on the right. There are not, of course, these are only the examples. But if we do so, we'll obtain another much larger and much broader family of hybrid organic inorganic materials. By changing the oxide to larger halide or complex ligands like cyanides, formates, or dicyanoamides, and so on and so forth, we still preserve the three-dimensional structure of connected octahedra, but we also will be able to produce much larger cavities in this structure, and we will be able to put much larger cations, even protonated amines. So in this new class of materials, because due to this changes, we will obtain new properties of the crystal structure. Some unconventional tilts and some unconventional columnar shifts will appear. We will be able to introduce the dipoles, the quadrupoles, and other molecules in it, and to study the properties. Here, I would like to focus on the three types of hybrid organic inorganic materials, on halides, formates, and hypophosphates, and the small amine, which is methyl hydrazinium, will I will put a methyl hydrazinium into this three type of inorganic components, inorganic substructures. So I'll start with halides. Why the halides are very extensively studied, and why they are so interesting. Please have a look at this best research cell efficiency chart, which is published each year and shows the materials which are used for engineering the solar cells, photovoltaic cells. And if we will have a closer look, we'll see that here, I mark it on yellow, we'll see materials which are called perovskite cells. And it is lead iodide with metal ammonium is the main, so it's an organic inorganic halide. It's a main component of this perovskite solar cells. And you see also here a huge increase in efficiency in the last year, which was not observed for other materials. So still the research on these materials is important. The research on halides is important just to obtain better and better, more stable and more efficient solar cells. This progress in last year was mainly due to the new technology which appeared. It's a tandem cell technology where we can use a sandwich composed of layers built of perovskites with different widths of band gaps. And this way we can more efficiently use or absorb the solar spectrum and more efficiently generate the the electrons and produce a current. And in halides, it is very easy to control the band gap just by simple chemical substitutions. Here we have examples of such substitutions and a graph when we can see how much the band gap changes when we change the X sides or the A sides as well as the B sides. Here, for the lowest band gaps, which are more interesting, the lead iodides or mixed lead and thin iodides leads. However, for the wider band gaps, we can play with chlorine, also and bromine, chlorine and bromine materials. And you can see here how the changes of the band gap also change the color of the photoluminescence in halides. But in this table, especially on this first position on the asides, there are only two amines. First one is metylamine, and the second one is formamidinium, formamidine, and the cation formamidinium. Only these two molecules are able to enter the perovskite cavity, which is present in lead iodides. So we can also mix some different amines on this A position, just to obtain better properties of better properties than the pure metylamine has, as it is pure metylamine is not stable, unfortunately, under the normal conditions, do not like humidity, and has a phase transition in the working condition of the cell. So if we here I just show the results for two different composition, the phase diagrams for two different composition. One for lead iodide, when we just added another molecule, which is ethylamine. Ethylamine do not form three-dimensional structure. It crystallizes in the chain structure. However, it is possible to introduce quite large amount of this molecule into the metylamine perovskite structure and to suppress the phase transition temperature from the cubic to the tetragonal phase, which is present here. And it is very important because we can decrease the temperature of the phase transition, and in the temperatures when the photovoltaic cell works, we will not have a phase transition, which is for engineering it is much better. And the second thing is that by addition of ethylamine, we can obtain much more stable materials. So these chemical substitutions may slightly modify the material, slightly modify the band gap, but also totally change the temperature behavior and the moisture resistivity, for instance. And here on the right side, there is another phase transition diagram when we played with this A side in lead bromide. And as you see here, also by changing, we were able to obtain actually a solid solution. And in the whole range of the substitutions, we can see how much the changes change the temperature evolution, the phase transition diagram, and the shift on or suppress toward lowered temperatures and the low symmetry phases. But playing with composition, it's not only thing that we do. It was interesting whether we can find another molecule which could enter the perovskite three-dimensional structure and be stable. And it appeared that there is such a molecule, is methylhydrazinium cation, which is shown here. We succeeded at obtaining two materials, pure bromine and pure bromine material, and a solid solution of chlorine and bromine. And both these materials crystallize in three-dimensional perovskite structure. In pure bromine, we have a phase transition at high temperatures to the disordered cubic phase, which is common for all perovskites, even for inorganic perovskites, when they have ideal cubic arrangement and very disordered amine inside. We can only see a sphere of diffused electron density inside this cavity. But with temperature lowering, we have a phase transition. Actually, in the solid solution, there are two-phase transition to lower symmetry phases. Both lower symmetry phases, also the room temperature phase, are polar, do not have the symmetry center. So this is a new finding because the symmetry for metallamine and the formamidinium, they crystallize in centrosymmetric structures. Here we have a polar arrangement of cations. And what is even more interesting, we see that the high temperature phase, which is of the orthorhombic symmetry, has even better polar arrangement of these molecules, which is surprising because usually with temperature increasing at higher temperatures, the amines start rotating and they lose polar properties. So here we have increase of the polarity at high temperature, and you can see here how the second harmonic generation increase in the phase in the orthorhombic phase, and it's lower in the low temperature phase. So we can obtain the switching of the second harmonic generation signal, and also maybe treat this material like sensor for the temperature. So why the structure of this? So another slide presenting the structure of this bromium, lead bromine or lead chlorine structures. Where I would like to focus on the octahedra. So this is a system of a three-dimensionally connected octahedra, but we can distinguish here two different layers. One, this gray one, which is a normal layer, I do say, and the second one, this violet one, or purple one, which is massively distorted. So from one point of view, the octahedra, the coordination of the lead in this position looks like octahedral, but when we will have a look on along C in other direction, we will see that these octahedral, these coordination spheres are massively distorted. And also we can study the distortion parameters and compare the distortion parameters with others for mamidinium and metallammonium. We'll see that the difference is huge, really huge. The distortion parameters are several times larger than for the normal perovskites. Why does it happen? Because in this material, the metal hydrazinium actually is too large to form the normal three-dimensional perovskite structure. Its tolerance factor is larger than 1. So from theoretically, this three-dimensional structure should not be formed, but we have here organic and inorganic compounds, so something which is different from the inorganic chemistry. And the metal hydrazinium, this NH2O group changes the environment around one of the lead and form the coordinate bonds, which are well known in the organic chemistry. So the distances here between lead and between nitrogen fits well the distances which are present in coordination chemistry of lead compounds. So we have something new in which comes from the inorganic part. But what will happen if we change one of this distorted layer? So if by changing the condition of synthesis and the stoichiometry, and we just exclude it from the structure, then we may obtain another material which have different stoichiometry. It's lead brommium 4, which has a layer structure, and it's also very interesting because we have a new material which has phase transitions, and what's even more important, has ferroelectric arrangement of polar arrangement of cations at room temperature, and features the ferroelectric properties. Here is the dielectric response of these materials measured in different directions. You can see here also the hysteresis loop and the material itself. So we can produce from normal wet chemistry nice single crystals which are stable up to around 500 K. So now let's switch to formates. Just by changing the halide ligand in the structure by formate ion, which is drawn here on the top of the slide, we may enlarge the cavity and have a space able to accommodate larger molecules. So up to now, the metal formate family are the largest ones. So there are a lot of new materials have been synthesized using this formate and different amines. And why this formate ligand is so attractive? Because it's not so large, so it's still capable of mediating ferro or antiferromagnetic coupling between the metal ions accommodating the B sites. It is also very good hydrogen bonding acceptor and has quite stiff and planar geometry, which of course is important from the point of view of the crystal structure and the possibility of formation on different structures. So the investigations on formates boosted after the paper of Jan, which was published in 2008, where in which paper he reported the ferroelectric and ferrimagnetic properties of dimethyl ammonium formate with different metals. Here we see results from the paper of Wang, when they show with his co-workers that at the transition temperature to the ferroelectric state, we can see the changes of the magnetic susceptibility, and we can also change the polarization of these materials in the broad temperature range, especially in the ferroelectric phase, by applying different magnetic fields. So a material with large magnetoelectric coupling was obtained. The metal formate perovskites usually or very often have order disorder phase transition, because in the high temperatures, the amines are disordered. They may rotate in the cavity of this perovskites. And one of the methods which we can observe these movements is broad dielectric spectroscopy. So usually in these materials, the relaxations is seen over the large width of frequencies and temperatures. Usually, the ferroelectric properties are evidenced just by the fact that we are able to reverse the pyroelectric current. It is very difficult to obtain the hysteresis loops, but some of them were also reported. And in the ferroelectric or in the polar phases, we can switch the signal of the second harmonic generation. So a huge family of compounds with nice ferroic properties, magnetoelectric coupling, easy to be synthesized, and quite stable. So here I will just show in more details the characteristic features of formates. Basing again on methyl hydrazinium cation, we were able to introduce the methyl hydrazinium into the four metal formates, and it appeared that these formates have two phase transitions. During this phase transition, we can reverse the pyroelectric current. So we have transitions from the high temperature centrosymmetric phase to a polar phase, to the two polar phases. So this is a characteristic crystal structure for formates. So high temperature disordered phase when we have a lot of orientational states available for amine. And we can also see this perovskite cavities here. And in the high temperature phase, we have a huge disorder. Amines may rotate along this easy threefold axis, but also along this not so easy, I would say, twofold axis. And with temperature decreasing, we can block this movement. And there is a phase transition to the low symmetry phase. We lose the symmetry center and have a polar arrangement of this amines, which gives us also ferroelectric. And we have also ferroelectric properties in this material because the current is maybe reversed. With further cooling, again, we can block the movement of the amines blocked totally, and at 100 K we have a well-ordered cationic substructure which interacts with hydrogen bond with this distorted metal organic framework. The phase transition are well visible on the Raman spectra, and what else? We also measured the magnetic properties for these metal hydrazinium compounds, and it occurred that they also have long range interaction, anti-magnetic interaction. Here we have antiferromagnetic properties for both materials. Of course, the temperature of the ordering, magnetic ordering, depends on the metal which was used for the synthesis. So now I will go to hypophosphites. Why hypophosphites? They are very similar to formates because we just changed this small formate to another slightly larger phosphate ligand just by changing carbon to phosphor. And you can see here slightly longer, but it's only 0.3 angstrom, so the change is not large. But what mostly influenced the structure of formates is the fact that this ligand is no longer planar, and is very flexible. So this OPO angle may change in a broad range of the angles. First reports on formates was actually 5 years ago, and the authors synthesized the first report on this hypophosphate was reported 5 years ago. And authors suggested that in this class of material we can obtain also very numerous phase transition because of the flexibility of this crystal structure. So depending of the cation, we can switch the crystal structure, and also it should respond with temperature lowering with some phase transition to probably ferroic states. Here is the delta parameter, which describes the deformation of the cubic cavity, and the larger this parameter, the deformation is also larger. So you can see here that in this bolded formates, this delta parameter is below 1, it's quite small, and for most hypophosphates, this distortion parameter is larger than 1, even approaches 10%. So this distortion of this crystal structure hypophosphates is much larger than distortion formates. Because there was no many hypophosphates, we just decided to synthesize new analogs and determine the physochemical properties. And after our study, we just add to the list of known hypophosphates this new red materials, which are listed here. I don't know how much time I have, so I will continue. So you can see here the topology of the manganese hypophosphate perovskite, which is actually common for most of hypophosphate materials.
I'm sorry?
Yes?
Yes, only one information. I think you have approximately 10 minutes.
10 minutes. Oh, super. Thank you very much. Thank you. So you can see here again, you can see here the topology of these materials, as well as placement of the amines in the cavities. And what is different in hypophosphates is the fact that at room temperature, all these amines are actually ordered, and most of them are not placed in the center of the cavity, what was characteristic to formates. So the structure of hypophosphates behave in a different way. We synthesized new materials with pyroledynium and ethylammonium, and it occurred that also the tolerance factors for these molecules are actually too large, too high to produce the perovskite structure, but it was possible to synthesize this material because of the flexibility of this OPO bonds. So this ligand the hypophosphate ligand may stretch, may change the type of the bonding from anti-anti to some anti-syn and so on and so forth. So it is possible to introduce larger amines to hypophosphates than to formates. All of them, this manganese crystal, have phase transition to the antiferromagnetic phase and have red photoluminescence. So another look at this on the crystal structure of the manganese hypophosphates, we can see the order state. We can see that the all hydrogen atoms from amines interact with the substructure, with the metal hypophosphate substructure. So perfect crystals without phase transitions, and what we can do with them is just we can see the optical behavior. So by changing the amine, we can tune the color of the photoluminescence, but actually all of them produce have a red or orange red or orange color of the photoluminescence. So just to obtain more functional material with phase transition and possibly with some ferroic arrangement, we again took this methyl hydrazinium cation, which both in halides and in formates gave us the acentric structure, acentric arrangement, polar arrangements, and we apply this cation to the hypophosphate structure, and to our surprise, we again obtained a totally ordered material at room temperature with amines which are displaced from the center of cavities and interact nicely with by the hydrogen bond with the hypophosphate structure. So just to compare with formate, you can see that in formate we have massively disordered cation, and in hypophosphate the inorganic part can very nicely adjust both to the size and both to the number of the active NH groups for hydrogen bonding, and to produce a stable ordered crystal. We wanted also to see what will happen if we mix hypophosphate with formate, and we did such an experiment, and it occurred that in the mixed system formate ligands only place here in this layer when we have anti-anti configuration modes, connection modes like here, and hypophosphates locate here along this line where we have an open OPO angle, and the connection mode change from anti-anti to more syn-syn. So again, the flexibility. Metal hydrazinium templated manganese hypophosphates is also antiferromagnetic material, and also has this orange-red photoluminescence, which shows quite nice temperature dependence and possibly may be useful for temperature sensing. And we are also able to find the mechanism of this photoluminescence, which is connected with the charge transfer from the oxygen ligands to the manganese centers. Then we just want to see what will happen if we change not the amine but the metal as well. So we produce a series of cobalt and cadmium formates. They all had this features which are also find for manganese hypophosphates. They were all ordered with distorted, massively distorted cavities, and they did not have a phase transitions. One of them was polar with small polarization, quite small response of the second harmonic generation, but we were not able to tell from the structural parameters why actually this one prefers crystallization in the polar state. All of them, so the cadmium analogs, all of them are have blue luminescence, which is asymmetric and broad, and due to this large distortion of the octahedra, which coordinate cadmium. And what is interesting here was the fact that one of them, with imidazolium, have clear ferromagnetic ordering with clear ferromagnetic hysteresis loop. The temperature of this ordering was actually quite low, was 10 K. In this large family, or in this new family of materials, only two experience phase transition. This is formamidinium cadmium hypophosphite, which was synthesized in our group, and formamidinium manganese hypophosphite, which was synthesized in this pioneering work. And this was the phase transition is evidenced on the X-ray diffraction images, as well as color. It's also present on colorimetric measurements. There is thermal anomaly and some dielectric relaxation process is also observed. Raman spectra have a lot of discontinuities at the phase transition temperature, so we have a clear phase transition. And what happens in this material? So at high temperature phase, in phase 1, the surrounding of the ions, of the cations, it's quite symmetrical. They are placed, they're not placed, but there is a mirror plane which passes through this cation, producing two equivalent position. And with temperature decreasing, there is a breaking of the symmetry. We lose this mirror plane, symmetry decreases, and we have now one ordered state in manganese hypophosphite. And actually, for the cadmium analog, we still have some two similar orientations, but with different occupancy factors. So we still have disorder. It's more statistical one, not dynamical, but it's still present because actually the inorganic part, this metal hypophosphate part, doesn't change much. Actually, the coordinates, the positions of the atoms of oxygen and the metals are almost the same like in the high temperature phase. So we have very weak changes or distortion in the structure. So I'd like to finish with the last slide, which shows the results which were obtained in the group of Professor Katrusiak. They did the pressure. They investigated the pressure changes of these materials and this formamidinium cadmium hypophosphite. And as you see here, the crystal structure of the hypophosphite is so nicely fitted actually to the ion at room temperature and zero pressure that we do not have a phase transition actually up to 4 gigapascal, which is for this organic inorganic materials really high pressure. Usually they have a phase transition under a much lower pressure, but the volume changes much, and without phase transition it's reduced almost more than 15% from the initial one, and that's 4 gigapascal. So I would like to summarize now my talk on the hypophosphites. It's a smaller group, it's the smallest group of the organic and inorganic perovskites, and due to the much higher flexibility of this metal hypophosphate framework compared to, for instance, to formate ones, mostly ordered and stable perovskite structures are formed, but we can also obtain three-dimensional structures for larger amines. And when we change, of course, the metal, we can tune the physical properties like magnetic response and optical properties. And perhaps it is perhaps the hypophosphites are not so interesting like the formates because they do not have a phase transition, but it is also because we found some polar phases. It means that it's maybe a nice platform also for searching for ferroelectric or multiferroic materials as well. And some general conclusions. The research on organic and inorganic perovskites is in progress and is extensive. New functionalities are discovered. And very last slide. We all know that these organic and inorganic materials are fragile, do not like humidity, water, but the progress in producing of thin layers, mesoporous structures, maybe will open the field for use of these materials also. And here is the results of production of small elements from the organic inorganic MAPI material by just inject printing solar cells. So we can produce some small modules using this perovskite solar cells, which actually work and may be introduced to the market. And thank you very much for your attention.
Okay, Professor, thank you very much for nice presentation. But I'm sorry, the presentation time exceeds too much. So I'd like to move on the next presentation. Okay?
Okay, of course.
I'm sorry, Professor. Yes, this is from Paweł Ławnicza from Organizing Committee. I think because we don't have the last speaker, so maybe one question. We have time for one short question. If anyone would like to ask.
Okay.
Okay, so if not, we can continue the session. So the next speaker, Miss Leila Farhat, and once again, thank you, Professor Anna Gagor, for a great speech. Thank you.
Thank you very much.